Hello everybody, you're very welcome to this episode of Programming and Algorithms. In this episode we're going to look at merge sort. Now merge sort was developed by John von Neumann in 1945. John von Neumann, born in 1903 and died in 1957, is very important in computer science. He was an extremely important mathematician and a very important computer scientist. Indeed, the way we typically create computers using a stored program method so that the data and program are stored in the same memory and with a single processor is called the von Neumann architecture, after John von Neumann, who helped a little bit Alan Turing and would have been very influential on Claude Shannon's work on information science and information theory. So von Neumann's merge sort uses a divide and conquer strategy. It has two steps in it. The first step is to keep splitting the array in half until we end up with subarrays of one element each. And because there's only one element in each subarray, they're sorted. And then we successively merge each subarray together, and we sort as we're merging. So let's look at an example of that. We start off with our old friend, our array, as usual. We split it in half, and then we split each half in half as well. And then we split each half in half again. So then we have 8 subarrays. Each subarray is sorted. The first subarray just has the number 44 in it, so that's sorted. The next subarray has the number 23 in it, and that's sorted because there's only one element in it. Now that's the splitting bit, which is fairly easy. The divide. Now let's look at the merging back element. We have our array again. Now we merge the first two elements together, 44 and 23, and then we sort them as 23 and 44. Then we take our next two elements, we merge them, and we sort them. We take the next two elements, we merge them, and there's no need to sort them because they're sorted already. So that's one step for those. And then we take the last two elements, and we merge them and sort them. So that's 4 subarrays all sorted. Now we take those 4 subarrays, and we merge them, and we sort that array. And we take the 2 subarrays and merge it into a 4-element array, and then we sort that. And then finally we take those 2 subarrays, we merge them, and we sort them. And we've got our array sorted. As we saw for shell sort, this process of sorting subparts first means that the final sort at the end will be a lot quicker. So if we look at the middle line there, we can see that a lot of the elements are kind of in the correct position already. So it's a quick sort because we've already got a lot of the work done. So let's look at our code. We'll declare our main merge sort program simply declares the array, calls merge sort passing in the array as a parameter, and then prints out the array. So let's see what merge sort does. Merge sort says, keep recursively splitting the array until we get down to one element. So as long as the length of the array is greater than 1, let's keep doing this thing of finding a midpoint in the array and creating 2 subarrays, the left half and the right half. The left half of the array is everything up to the midpoint. The right half of the array is one past the midpoint to the end of the array, and we're using, we're splitting like that. And then what we're doing is we're recursively calling the merge sort program we've just declared for the left half of the array and the right half of the array. So our first recursive call to the left half, it'll pass that in, it'll split left half into 2 halves again, call merge sort left half again, split it, and keep doing that recursively until it gets down to one element. Each time we call merge sort though, the current version of that is pushed onto a stack. Then when we call that merge sort again, it's pushed onto another stack called, and then we pop those elements back off this stack to complete each of the merge sort algorithm. So we're dividing the array in half and recursively calling for each half, and we split down until we get a single array. Then we create a few variables, a counter for the left, a counter for the right, and the main array. And then what we say is, compare the value that's in the element on the left to the element on the right. and keep looping around as long as we've values both on the element and on the right, and compare the first element on the left array to the first element on the right. If the first element on the left array is smaller, then write that into the main array in its position. If the first element on the right is smaller, then write that into the main array. So compare the first element of each subarrays, and whichever is smaller gets written into the main array in its position, then the next element that's smaller gets written into its position, then the next element. And keep going while there's values in both arrays. That is not to say keep going while there's no elements, while there's elements left. If whichever runs out first, if all the elements from the right half of the array gets written into the main array, then stop there, or if all the elements in the left half, stop there. So then what we do is we check what's left. So we'll have written out some of the elements, let's say in the right half of the array, and all of them from the left half. So then we just need to write out all the remaining elements from the left half in. The opposite case, we might have written all of the elements from the left half of the array into the main array and some of the right elements. So then we need to write the rest of the right half of the elements in. So we have two loops here. Either there's values left in the left half of the array or values left in the right half of the array. Whichever it is, write them into the main array then. So this is fiddly stuff because this is the program done. What we need to remember is, because this is recursively being done, we do a split and then we've just one element of each. Every time we call merge sort recursively within that split, we're pushing that call onto a stack that the operating system remembers. So then when we get down to a single array, we're popping those values back up and we're merging and sorting as we're going along, as we can see here. In terms of the complexity of merge sort, like shell sort, the best case scenario is n. So if the array is 10 elements long, it might take as little as 10 exchanges. Our average complexity though is n log n, or n log to the base 2n. So if it's 10 elements long, it'll be about 30 computations, and our worst case scenario, like shell sort again, is order n log n as well. So that is substantially shorter. Again, if we think of the case of 1,000 elements, instead of taking 1,000,000 iterations, it's only going to take 10,000 iterations on average with a merge sort. So this is much more effective than an insertion sort, or a bubble sort, or a selection sort for that matter. So thanks very much. We'll see you on the next episode.